And we're going to start talking now about inverse trig functions. And it's a bit of a, well, I probably shouldn't make value judgments, but well, whatever. It's a bit of a pain. You're going to have to memorize some new derivatives, and you're going to have to memorize some new integrals, and the integrals are kind of messy. So when you use them, you usually have to do stuff to them and do U substitution, but it's unavoidable. So, I mean, at least the good news, there is good news, which is that even though there are 6 inverse trig functions, only 3 of them routinely get used in calculus, and we'll only cover those trig functions. So at least we don't have to learn all of them. So the world's quickest review of inverse trig functions, just because I know some of you probably haven't seen this since high school, maybe. An inverse of a function can be defined formally in terms of composition. 2 functions are inverses if when we compose them, they cancel each other out, and we are just left with x. The more probably useful sort of day-to-day way of thinking about things is that functions and their inverses undo one another. Like in the real world, we can have a function that converts from Celsius to Fahrenheit, and we can have a function that converts from Fahrenheit to Celsius. And you know, if you take 0 degrees Celsius and you convert it into Fahrenheit, and then we take 32 degrees Fahrenheit and we convert it back to Celsius. These 2 things undo each other, and we're back where we started at 0 degrees Celsius. And not every function has an inverse. An inverse of function has to be 1-to-1. If f of b equals f of a, that should imply that b equals a. So, you know, x squared is not 1-to-1 and does not have an inverse, because 2 goes to 4 and -2 goes to 4, and 2 and -2, of course, are not the same number. More relevant to what we're talking about today, none of the trig functions have inverses. You know, the sine of x, that sends 0 to 0. It also sends 2 pi to 0. 0 and 2 pi are not the same thing. And this is a problem. It's a problem for both these functions, actually. It's a problem for x squared, and it's a problem for the sine, because inverses are how we solve algebraic expressions. Like, we start solving equations long before we hear the word inverse, so we normally don't think of it in that way. But like addition and subtraction are inverses. So if you have this, if you think of this as a function, we've got a +2 function here. Its inverse is the -2 function. And the inverse allows us to solve for x. If we have x cubed equals 8, x cubed has an inverse, it's the cubed root. On the left, here you see this conception of the inverse. We've got that composition and it cancels out and it leaves us with x. On the right, well, the cubed root of 8 is 2, but the important point is that we took the cubed root of both sides. So x squared equals 4, we want to be able to solve this just like we solved x cubed equals 8. But x squared doesn't have an inverse. And I don't think I've ever seen this made explicit in a textbook, but the way we deal with x squared and the way we deal with the trig functions is identical. And that's to find a solution. There's no inverse, but there's an inverse like operation, which is the square root. Doing this gives us a solution. There's another solution that we haven't gotten, which is what? -2. -2. But so we get a solution, and then we say, well, if we want the other solutions, we can get them. We can put a plus or minus sign there. And one way of thinking about this, if you wanted to, is that you could think of this in terms of a domain restriction. You could say, well, there's x squared, and here's 4, and x squared equals 4 has 2 solutions, and x squared is not invertible because of the horizontal line test, which I did not put on the whiteboard, but the horizontal line test says that if you can draw a horizontal line and it hits the function at more than one place, then no inverse exists. So one way of thinking about this is taking x squared and restricting the domain, erasing part of this curve. And now that new function is invertible, and we call the inverse the square root. So in order to deal with the issue that x squared is not invertible, we restrict its domain on an interval where it is invertible. And this is also how we deal with the trig functions. The trig functions don't have inverses, but also we need the trig functions to have inverses. Just like the square function, we want to be able to solve equations. You know, we want to be able to solve. And we define an inverse trig function that's the inverse of the sign on an interval. We say, let me make sure I remember this restriction. The sign starts in the, yes. We say, well, the sine function looks like that. And we want to know when the sine function equals 1/2. And the sine function equals 1/2 in an infinite number of places. But in order to solve this equation, we can take the sine function and we can restrict it on this interval where it is invertible, and we can define the inverse on this interval. And then if using the inverse, we can find a solution to sine of x equals 1/2. And it's not the only solution. There are an infinite number of solutions. And if we want other solutions, we have to mess around. But for the purposes of this class, we're not doing that. We just sort of need to know basically on a fundamental level what the inverse sign is. And it's the inverse of a sign on an interval. Even things like, you know, in trigonometry, you of course were made to, at some point, learn the interval that these restrictions live on. Even that, we don't really need to worry about in calculus. We just need to know what these things are, basically. And, oh, just a heads up, these inverse trig functions have two pieces of notation, and I feel like this is one of the very few situations where I kind of allow myself to be intentionally old-fashioned. Here are the notations for the inverse sine function. And as I say, I think it's very old-fashioned now, but this is what I learned as a child, and this is what I continue to use. So if you're getting, you know, watching videos online or whatever, and you see a different notation, those are the same thing. They're just written differently. And in calculus, as I say, only 3 of the inverse trig functions are going to really be interesting. And they're probably not the 3 that you would imagine. You know, high school trig, it's the sine, cosine, tangent. For our purposes, the cosine isn't going to be very important, and we're going to want to look at the arcsine, the arctangent, and the arcsecant. And we can just start talking about these one by one. Talk about learning these. It's about to become very evident that I do not actually have these committed to memory myself. But there's the derivative of the arcsine, and it seems implausible, sort of. I mean, again, it's just I never quite know what to make of it, that you have these functions like the inverse trig functions, and they're defined so weirdly, and it seems like there should be no earthly reason that they have a straightforward derivative that you can just write down, but there's the derivative of the arcsine. It carries, notice, x has to be between -1 and 1, otherwise we'd have the square root of a negative number, but the arcsine's domain is -1 to 1, so that's what we'd expect. X was always stuck on this interval. And we can do, whatever sort of example we might want to do. I guess something involving the chain rule would maybe be apropos. And if we want the derivative of the arcsine of x squared, it's hopefully, it's new, but it's hopefully all very familiar. We've got this function, the arcsine, and then inside the arcsine, we have a different function. So we take the derivative of the outside function. We stick the inside function inside of it. And then we multiply by the derivative of the inside function. And we could clean this up, of course. X squared squared is x to the 4th and so on, but fundamentally this is what we're doing. We're using the chain rule in what I hope is a very familiar way. Really though, and maybe unexpectedly, the reason you might wonder, we could have talked about this in 151 if we wanted to. It's just a derivative. We did the other derivatives back then. But what we're really interested in here is not the derivative, but the integral that the derivative gets us. So every statement about a derivative is also a statement about an antiderivative. A statement about indefinite integrals. So the indefinite integral of 1 over the square root of 1 minus x squared dx is the arcsine. And this might seem kind of, I'm trying to think of a word here. Inapplicable, in the sense that you might sort of wonder, well, that integral looks really messy. Why would you have the integral of 1 over the square root of 1 minus x squared? But expressions like this, like the square root of 1 minus x squared, show up more often than you'd think because you can get them from the Pythagorean theorem. So if you have a right triangle, let's see, it says a squared plus b squared equals 1. So a is the square root of 1 minus b squared. So if this is 1 and this is x, then that square root is going to show up in this triangle. So these show up fairly frequently in applications of calculus to engineering and geometry. They are something that we have to deal with. And you might then look at this and you might say, well, this is pretty limiting as well, because what if the hypotenuse isn't 1? What if the hypotenuse is something else? But we can't, or what if this isn't x? What if this is, I don't know, 7 times x? And we can deal with these complications using algebra and U substitution. And it's one of the, in my opinion, one of the less fascinating things we do in this class, but it can't really be helped. So what if instead of 1 minus x squared, we have a different number? What if we have 4 minus x squared? I've started out with 4. 4 is a perfect square, but the technique we're going to use doesn't require us to have a perfect square. And we say, well, I have a 4. I need a 1. Is there a way to go from having a 4 minus a square to having a 1 minus a square? Well, we could do this, and at first blush, it might seem like we're just kind of kicking the problem down the road, because our formula has a 1 here, but it also just has an x squared. So you've turned the 4 into a 1, but you've also turned the x squared into something else. But that's okay, as we're about to see. We can use the fact that the square root of a product is the product of the square root. To get that 4 out of the square root. And in fact, because that gives us a fraction, that gives us a constant, I should say, we can get it entirely out of the integral. Is that step clear to everybody? And then we say, all right, well, this isn't quite what we want, but it's not that bad. We're off by a constant, we're off by a 1/4. And the trick is to write this as a perfect square and then use a U substitution, a small U substitution. This is x over 2 squared that we have here. Maybe I'll write that as 1/2 x squared. And if we do a little U substitution, if we let U be 1/2 x, then du is 1/2 dx. And we have that dx, obviously. We don't have the 1/2, but we're off by a constant, so we can, I mean, again, I just deal with things like that, put the 1/2 in and then divide by it. I know from the homework that some students prefer to do work down here. I've never learned to do it that way, but do whatever works for you. Then this 2 will pull right out. And we have this 1 over the square root of 1 minus u squared. This 2 over 2 is 1. It goes away. The integral is the arcsine. So this is the arcsine of, let me see, u was 1/2 x plus c. So that's how these work. And I mean, well, we'll do an example Wednesday, but I mean, now that we have this idea of taking the x squared, and if we have a number in front of it, it doesn't really matter. We just write it as a perfect square. I mean, it's hopefully pretty clear that if we had something like that, it wouldn't really fundamentally change the problem. Well, as I say, we can do an example like that on Wednesday. It's also true, I mean, I made my life a little easier by starting with a perfect square, but if we had a 5 here, it wouldn't fundamentally change the problem. We'd pull the 5 out, and then we'd have 1 over 5, and this can still be done using U substitution. We can still write this as a perfect square. It's just to write 5 as a square, you need the square root of 5. You know, to write 4 as a square, we needed the square root of 4. The square root of 4 was nice, it was 2, but there's nothing fundamentally different here. You know, we'll let u be that, and du will be this, and then we can put that 1 over the square root of 5 in, and we can also put its reciprocal in. And now we have the arcsine, just like we did before. So the things that do matter, the subtraction has to be being done in this order. We need the number on the left and the square on the right. If those are reversed, we have a different inverse trig function that we need to use, but we can, with 6 minutes remaining, it doesn't make sense to proceed to the arctangent. We'll do that Wednesday. I mean, we'll probably do the arcsecant Wednesday as well, and then I'll have to think what we want to do Thursday.